In 8.7, we're looking at exponential growth and decay. So here we have a little table that you're going to want to write down. It's parts of growth and decay function. So over here on the left, we have our growth function, where A represents your initial amount and R is your rate. And then on the right, we have our decay function, where once again, A is your initial amount and R is your rate. Notice the only difference here is in our growth, we're adding 1 in R, and in our decay, we're subtracting 1 in R. So another kind of table that you want to write down is we have another way of representing our exponential growth and decay, where if b is greater than 1, then that means we're going to have a growth function. If b is between 0 and 1, that means we'll have a decay function. So here is our first example. So our type of function we find by looking here. This is that b, and since it's greater than 1, this is a growth. Our rate of growth or decay is also that number. So 1 and 900. Now, you have to be careful. Sometimes you're going to be asked for your rate of growth, and sometimes you're just going to be asked for the rate. When I'm asked for just the rate, I'm going to take 1 minus, we're going to take our growth, 1.09, and subtract 1 from it, which means our growth is 900th. And then your initial amount is that number in front, that A, which is 24. Let's look at another one. We look here, that is bigger than 1, so this is a growth with a growth rate of 2.3. And then the rate itself, we take that 2.3 and subtract 1. So we get 1.3. And then our initial amount was that 1.35. All right, here's another example. It's a decay function because this is less than 1. So our rate of decay is 0.23. Now, because it's decay, when we're finding our rate, I have to take 1 minus that 0.23, which is going to equal 0.77. And then our initial amount is that number in front. So I think the most challenging part is differentiating between your rate of growth or decay and just the regular rate in general. So now when we're talking about specific populations, it's a very similar formula. The only difference is T, where T represents our number of years. So we have the population of Arizona was 5.6 million in 2000 with a growth rate of 2.1% annually. What will the population be in 2020 if the growth rate stays the same? So we have 5.6 million is our initial amount. then 1 plus, now this is where you have to be careful. This is a percent, so we need to change it to a decimal. So 2.1% would actually equal 0.021. So if you don't remember how to do that, you move your decimal 2 places left and fill in with the 0 if necessary. And then to the t power, we need to figure out how many years are from 2000 to 2020. Well, that would be 20 years. From here, we would take this and plug it into a calculator, which I've already done. And we get 7 point, we'll do 2 decimal places, 7.82. And that's in millions. Because we started with 5.16. So this is what that population would be. So here's another one. The population of Coronado was 4.23 million in 2000 with a growth rate of 1.75 annually. What will the population be in 2020? So we start with our 4.23 million. Now we have to figure out what is that growth rate. So 1.75%. If I move the decimal twice, is 0.0175. And then t from 2000 to 2020 is 20 years. So a very similar formula. So I'm going to change the pieces of this. We're starting with 4.23 and we're adding 0.0175. So let's keep it 2 decimal places, and that would be 5.98. So it's approximately 0.98, and once again we are still in millions. And that is our population growth and decay.